Go to the mode shape. Understanding mode shape, I think if you are those who have seen those videos, then you can imagine very well. If you want, I'll put those videos also next class, tomorrow class. Here live demonstration will do those videos. So now we have the, if you come back to the our characteristic equation, in static analysis we have kx is equal to f, that is the equilibrium equation. When come to dynamic analysis, we have different set of equation, that k minus lambda into m into xi is equal to 0. That is the equilibrium equation. So that means k is stiffness matrix, that is a global stiffness matrix, m is mass matrix, the lambda is the eigenvalue. In mathematics you are saying it is eigenvalue. So eigenvalue is nothing but natural frequency, square of the natural frequency. Your lambda is nothing but omega square. It is a natural frequency. So now you are taking the x now. So k matrix is now, this is a general equation. It is not in the matrix notation. Now I am writing, just I added one more step. So where k is global stiffness matrix, m is global mass matter. Already we have the lambda I. There are two mode of vibration, first mode of vibration as well as second mode of vibration. In the first mode of vibration is referred as just it moves forward and backward, that is referred as rigid body motion. And second mode of vibration, there may be flexing. The flexing or twisting of the bar will take place. That is normally referred as flexing of the bar. So that we'll discuss later. So we have two values for the lambda. In simple, we have lambda I. We have two values for the lambda I. This is lambda I. The lambda has two values now. If you come back to this equation, we have lambda 1 and lambda 2. Now you are substituting those values here. Same set of equation you are using. The lambda I is equal to lambda 1 in the one case, and one more case lambda I is equal to lambda 2. The first case you are considering, the first case is lambda I is equal to lambda 1. So this already value, we have the lambda 1 value. See here, lambda 1 is equal to 0.102 into 10 to the power of 11. That's the lambda 1 value. So now in this equation, you are substituting lambda 1 value. So now you have to go back and I not use it. I am directly use this equation. We can come back. I think here we have the equation. This equation is referred as A. So this equation, we have lambda. The lambda has two values, the lambda 1 and lambda 2. In this equation, you are substituting lambda is equal to lambda 1. We have lambda 1 is equal to 0.102 into 10 to the power of 11. Same equation, but here you have u1, u2. You have u1 and u2. Go back and check here. I think here somewhere. So now you have the equation A. So in the equation A, we have this matrix is taken from equation A into u2 and u3. So wherever lambda is there in equation A, it is replaced by lambda 1. That's all. Here we have the equation. We have lambda here also lambda, and finally wherever lambda is there, lambda is replaced. In the first case, the lambda is replaced by lambda 1. That is referred as fundamental mode of vibration or rigid mode of vibration. In the second case, the lambda is replaced by lambda 2. That we will discuss later. First case, you are concentrating on the rigid body motion or first mode of vibration. So now what is the unknown is your u2 and u3 are unknown. You are not finding out the u2 value and u3 value. In your static analysis, you are going to determine, so what is the value of u2 and what is the value of u3. But in the dynamic analysis, the displacement will be changes with respect to time. You are familiar with the vibration of cantilever beam. The cantilever beam moves up and down. It is not a static deflection. If you put 1 kg of weight on the tip of the cantilever beam, it will deflect by, let it be 10 mm. The deflection remains same in the static analysis. But when you come to dynamic analysis, the cantilever beam moves up and down. You've done some experiment in your physics lab also. You are used some maximum displacement, transverse displacement of the cantilever beam. In the case of machine design 1 or machine design 2 also, there are a set of equation. What is the maximum displacement at the tip of the cantilever beam? That equation gives only the static deflection value, not dynamic deflection value. In the case of dynamic deflection, the displacement will be changes with respect to time. Vibration means your displacement will be changes with respect to time. If there is no change of displacement, then it will comes under the static analysis. Now you are not going to find out what is the value of U2 or what is the value of U3. Instead of that, when U2 is displaced by 1 mm, so what is the displacement of U3? If we come back to, because you have to understand some concept here. So imagine this is node 1 is fixed, there is no displacement. It's a fixed means no displacement. Your U1 is equal to 0, there is no question here. When you come to U2, so when suppose, an example I am giving, when U2, node 2 is moved by 1 mm, so what is the displacement of node 3? Or suppose node 2 is moved by 3 mm, so what is the displacement at node 3? Or if suppose node 2 is displaced by 10 mm, so what is the displacement, corresponding displacement of node 3? So once you know that, that is nothing but from that we can get the mode shape. Same thing you are going to do. So here we have U2 and U3. You are not going to find out the U2 and U3 in simple mathematically if you want to say. So you are getting the relationship between the U2 and U3. What is the relationship? So we have 2 by 2 matrix. So once you simplify this, if we expand this 5.279 into U2 minus 4.272 into U3, that's equal to 0. We will get one equation you can see here. 5.279 U2 minus 4.272 U3 is equal to 0. That's one equation. Then one more equation is 7.097 into U2 plus 2.194 into U3. That's equal to 0. That's a one more set of equations. This is a one more set of equation. From that you are getting two equations. So these are the equations. Then one more observation you have to remember here. You are putting 1. So 1 is not the element 1. Here superscript 1 is not related to element 1. That is related to your lambda. You have taken the lambda is equal to lambda 1. Lambda is nothing but we have differential this quadratic equation. We have two solutions for the quadratic equation. So one solution is lambda 1 value and one more the solution is lambda 2. So you are considering the lambda 1 value. Hence you are putting superscript as 1. It is not nothing to deal with the element. You are not talking about the element level. So you are considering lambda 1. Hence you are considering this as 1 1. Everywhere you are putting 1 1. So 1 1 is referred to your lambda 1. By considering only the first root of the equation, you are getting here. So this is the first equation. I can write first equation as, by using this equation we can simplify it further. From that equation, from the first equation or second equation, we can get one relation between U1 and U2. It is not like your regular solving the two equations. In the static analysis, what you are doing is, so in the static analysis, what you have done in the case of bar is, we have matrix. By using your calculator, we can find out U2 and U3. But in our case, so what is the determinant of this matrix is 0. This determinant of this matrix is 0. So that already you have discussed here. Here, determinant of this matrix is equal to 0. Then U2 and U3 are not independent. The U2 is moved by independently and U3 also moved independently. It is like nothing but your trains. Train, if you are easy to understand is, you have train bogie. The bogie 1 is moved independent. There is a relative motion between bogie 1 and bogie 2. Because there is a flexible coupling between bogie 1 and bogie 2. If bogie 1 and bogie 2 are joined by the rigid coupling, then there is no the relative motion. But that is not possible. We require flexible coupling itself. That means if bogie 1 is moved by the velocity of the bogie 1 is, let it be some 10 meter per second. and velocity of the bogie 2 may be 9.99 meter per second. There is a relative motion. That relative motion we are interested in the case of vibration. But when you come to static analysis, straight away we can, by using your calculator, solving these two equations, we can find out U2 and U3. But when you come to dynamic analysis, you are not going to find out the U2 value separately and U3 value separately. Just you are going to find out the relationship between U2 and U3. So don't try to find out what is the U2 value and what is the U3 value. You can use the first equation or second equation. By using first equation, second equation, you can get the relationship between U1 and U2 or U2 and U3, because U1 is 0. Now you can say that, so U3 is equal to 1.23. You are considering the first equation. Notes I have given on the right side. I put some notes. The comment also on right side, so you can understand better what I am explaining. Some point I am putting the notes also, so you can understand better. You can consider the first equation or second equation. We have U3 is equal to 5.279 divided by 4.272. So if you divide that, you will get U3 is equal to 1.26236. So that means if U3, we can get it here. That is best. X of 1. So x of 1 is U2 and U3, because U1 is equal to 0. You are familiar, because U1 is fixed at node 1. Node 1 is fixed, hence U1 is equal to 0. So when U1 is equal to 0, you have to find out U2 and U3. This is your displacement vector. This value will be changes. U2 and U3 value will be changes in the case of dynamic analysis. In the case of static analysis, you are getting U2 one value and U3 one more value. But in the case of dynamic analysis, so those values are changes continuously. Hence, we are getting different value. That's U2 is as usual you are keeping, and U3 is equal to, from this equation you are writing 1.236 U2. Then you are taking U2 outside. Then you are getting 1 and 1.236. The meaning of this is when U2 node 2 is displaced by 1 mm, node 3 is displaced by 1.236 mm. You can see here. So now it is x to U2. If U2 is moved by 1 mm, this node 2 is moved by 1 mm, the node 3 is moved by 1.236 mm. That is the meaning, because don't try to find out U2 and U3 value. In the dynamic analysis, you are writing your x2 of 1 and x3 of 1 is equal to x2 of 1.236. When node 2 is moved by 1 unit distance, node 3 is moved by 1.36 mm. That is the relative movement between node 2 and node 3. Same thing is shown here. This is mode 1. When node 2 is moved by 1 mm, node 3 is moved by 1.236 mm, or you can say in terms of unit. There is no unit here. There is only relative motion you are specifying. If node 2 is moved by 1 meter, node 3 is moved by 1.236. That same thing you can see here. So note, you don't think that it is moves in the transverse direction. The displacement of the node 2 is given by U of 2 at 1, and displacement of node 3 is given by U3 of 1. So 1 is referred to, you are taken the lambda 1 value. So when node 2 is moved by 1 mm, node 3 is moved by 1.236 for lambda 1. Now if you consider one more eigenvalue, the one more eigenvalue is your lambda 2. So once again you have to go back in the equation A. So wherever lambda is there, you have to substitute by, here we have lambda in the equation A. So wherever there is a lambda is there, that lambda you have to substitute it by lambda 2. Here also lambda 2, here also lambda 2, here also lambda 2. I think here also lambda 2, there may be one term may be missing here. So once you substitute in that equation, now first part is over. So in the first mode of vibration, you are considering lambda 1. Now you are considering the lambda 2 in the equation 2. Then you have to simplify. After substitution, you have to put what is the lambda 2. You have to multiply. You have to simplify. After simplification, etc., you will get one more set of equation for lambda 2. You are using the subscript 2. It is not related to the element. it is you are going for the second mode of vibration, or you are considering the lambda 2, hence you are putting the subscript. When lambda 2 is considered, or it is running at second mode of vibration, you have the different frequency. First mode, we have the different frequency. The first mode of vibration, frequency is 16065 hertz. When you come to second mode of vibration, frequency is 54209. So when frequency is very high, the vibration, the mode of vibration, way in which the shaft vibrate, so that also changes. In general concept, you remember, in simple way, in fan when running at 1000 rpm, the deflection pattern may be different. So when same fan is running at 5000 rpm, the bending, flexing, the complete vibration level, the pattern of vibration, everything will be same. So first, once you substitute lambda 1, we are getting one pattern of vibration or mode of vibration. In the similar way, when frequency is higher, the second mode of vibration is at a 54209 height. The mode of vibration is totally different, or pattern of vibration is totally different. For that, you have to go for substituting you are going for substituting lambda 2. The lambda 1, we have different frequency, so their pattern of vibration of the bar is different. Once you substitute lambda 2, that is higher frequency. At higher frequency, the vibration level is different. In simple way, even automotives also you can understand better. When vehicle is moving at low speed, when vehicle is moving at low speed, the vibration level will be different. When vehicle is moving at higher speed, then again vibration level will be different. In simple way, to understand better what is lambda 1 and lambda 2, the lambda 1 correspond to lower frequency, lambda 2 correspond to higher frequency. So at lower frequency, vibration pattern is different, especially lower frequency or at lower speed, the vibration may be very high, especially some cars, etc. Vibration may be very high. Even when you're starting the buses also, vibration level may be very high. But once it reaches steady state, the vibration pattern only changes. Or when frequency or speed changes, if speed changes, frequency of vibration also changes. We have the relationship between frequency and speed. As speed changes, the pattern of vibration also changes, or characteristics of the vibration of the vehicle or any structure also changes. At lower frequency, you are getting this pattern. At higher frequency, what is the vibration level? What is the pattern of vibration that we can get from substituting lambda 2 value? So once you substitute lambda 2, and if we simplify, we'll get the relationship between the displacement at node 2 and displacement at node 3. But in general, you have to remember, in the static analysis, the straight away you are getting the value of U2. U2 is constant for the static analysis, but U3 is also constant for the static analysis. But dynamic analysis, the U2 and U3 will be changes with respect to time. Most of the time, you are writing x of t. The x of t means the displacement will be changes with respect to time. Here also, U2 is also changes with respect to time, and U3 also changes with respect to time. So those two relationship you have done. You have after the multiplication, it is a 2 by 2 matrix. You get two equations. Those two equations are given here. If you consider the first equation or second equation, you get relationship between U3 and U2. I think if you take U3 is equal to 22.95 divided by 7.097. So finally, you're getting this equation. This is the second mode of vibration. The second mode of vibration is U2 and U3, 2 and 3. And if you simplification, etc. So U2 value you are substituting as it is. The U3 is minus here. Minus U2 into 1 minus 3.23. Or in simple way, we can say that, so when the node 2 is moved by, it's a forward movement. Don't think that it is not a cantilever beam. In the case of cantilever beam, there is a transverse movement. In the case of bar, you are talking about longitudinal vibration of the bar. When node 2 is moved by 1 mm in the longitudinal direction, this direction, and node 3 is moved in the reverse direction, because we are getting a negative here. So understanding this vector is, this is a modal vector, normally after the modal vector. Understanding this for longitudinal vibration of the bar is when node 2 is moved by 1 mm. So 1 mm in the forward direction. So node 3 is moved by minus 3.23 mm in the reverse direction or in the negative direction. Suppose node 2 is moved by 10 mm and node 3 is again moved by 32.3 mm, not in the forward direction, it is in the reverse direction. That those things you can observe. If you closely observe the the train bogies, sometimes the one bogie is moving in forward direction, especially in the junction when you're slowing down the speed of the train. The one bogie is trying to move in the one direction, another bogie is slightly moving in the opposite direction for 1 feet distance or 2 feet distance. In the similar way, so when node 2 is moved by 10 mm in the forward direction, node 3 also there is a displacement. The node 3 is displaced by 32.3 mm, not in the forward direction. It is moves along the in the opposite direction. That is the second mode of vibration. If you see those videos, please see those videos. You will understand better. If possible, I'll put it in the tomorrow's slide. I'll put. So try to understand the difference. I think try to understand the understanding the difference between static analysis and dynamic analysis. Conclusion is in the static analysis we have KQ is equal to F, but when you come to dynamic analysis we have Q double dot plus KQ is equal to F. So for dynamic analysis for the forced vibration, but you are dealing with only free vibration. For the free vibration, on the right hand side there is no external forces. Don't think that when there is no external forces, how the system will vibrate. The system is triggered only when t is equal to 0. Only at the initial time t is equal to 0, system is triggered. Or in simple example is, if you start the vehicle and stop it, so that is the free vibration. Even after stopping also, vehicle will start vibrating with certain velocity, a certain amplitude of vibration. Slowly amplitude of vibration will decreases and finally come to the 0. That is the free vibration. If you start the vehicle, keep it in the starting mode only, let it run for a few hours. So that comes under the forced vibration. If you start and stop, then each and every component will vibrate by its own. When t is equal to 0, you are starting. Then you are exciting the structure, you are putting the energy into the structure. Once you put the energy into the structure, energy is absorbed by the material. That is nothing but kinetic energy. It will be stored in the form of elastic energy or deformation energy. Even though you are removing the excitation, even though if you stop the engine itself, still system will vibrate. The simple example means you can pull the cantilever beam. So after leaving also it will start vibrating and finally it comes to 0. That is nothing but a free vibration. So forced vibration is nothing but when vehicle is running continuously, the vehicle is triggered or excited continuously by the engine. That comes under the forced vibration. In the case of forced vibration, we have mx double dot plus kx is equal to f of t, where f of t is equal to 0. But in your as per syllabus, you are considering only the free vibration. We have mx double dot plus kx is equal to 0. So k is stiffness matrix, m is the mass matrix for the bar element. K matrix for the bar element is you are familiar, already you studied in the second module. The only difference is, so you have to remember the mass matrix for the bar element. Then by using kx, mx double dot plus kx is equal to 0, we have a characteristic equation or eigen value. Those equations you have written a minus lambda into b is equal to 0. That's the characteristic equation. So in come to vibration, a is replaced by k, and lambda is nothing but the omega square, and b is nothing but mass matrix. Once we know the global k matrix and global k matrix, it is global k matrix is nothing but a global stiffness matrix. Then we require global mass matrix. Once you substitute k minus lambda into m, we are getting the value of lambda. From the lambda we can get the first natural frequency f1 and second natural frequency f2. Correspond to f1 and f2 or lambda 1 and lambda 2. You have to find out the modal shape m1 in this modal shape. Those modal shape you are shown at the last two diagrams represent the how the bar node 1 and node 2 road displaced. There is a relative displacement between node 2 and node 3. once you are able to represent the relative displacement between node 2 and node 3, that itself is the modal shape. Please see those videos, around 3 to 4 videos are sent. So I think you can understand better. Those are the practical demos they have demonstrated. So with that, I'll conclude today. Thanks. So I think if we have any doubt, I think we can clarify. Tomorrow I am starting with the dynamic analysis of the beam. After tomorrow again we are doing one problems on the beam. Again, beams also, there is a stiffness matrix. That stiffness matrix already you have studied. Then mass matrix will be changed. That's all. There is no much difference between the dynamic analysis of the beam. Only mass matrix for the beam you have to remember. If you remember mass matrix for the beam as well as mass matrix for the bar element, definitely we can expect one question from module 5, either from a bar or from the beam. Only two equations you have to remember. One, mass matrix for the beam, mass matrix for the bar. The stiffness matrix for the beam already you studied in module 3, and stiffness matrix for the bar element you studied in module 2. Those already you have studied. Only mass matrix for bar element you have to remember, mass matrix for the beam element you have to remember. If you know those two, you can solve the dynamic analysis of the bar problem as well as dynamic analysis of the beam problem. Same procedure you have to follow. I hope you understand. But one thing is, I think today or tomorrow I will put the notes in the Google Classroom. I'll share it in the Google Classroom. So try to do this problem by yourself. Then you may get some difficulty. Those difficulty we can discuss. Even tomorrow also, we are starting with the same dynamic analysis of beam. If you have any difficulties or any doubt, you can clarify. So now also you can clarify. If you have, I'll wait for a few minutes or few seconds. If you have any doubt, you can clarify now. So otherwise you can leave. The session is over now. If you have the doubt, so you can clarify now. This is a time for